Right. All right, guys. Today is going to be a lot of calculation based. And before you do the calculation, of course, you need to understand what your calculation is going to be for, right? Today we're basically going to learn about the difference between thermal capacity, specific heat capacity. Then after that, we'll also learn about the energy formulas here. We'll also learn about latent heat of vaporization and fusion. Then we're going to do 1001 calculations here. Okay, so without further ado, let's begin, starting off with understanding what specific heat capacity is first. Now today, if you want to understand what specific capacity is, not specific capacity, let's talk about heat capacity first. Heat capacity. In layman terms today, if you want to understand heat capacity is basically something that requires a certain amount of energy to raise the temperature. For example, today, if I say that a certain object has low heat capacity, it means to say it is very easy to heat up. If I say something that has very high heat capacity, it means to say it is something that is very hard to heat up. For example, today, if let's say you guys ever cooked Maggi mee before, right? We'll be talking about Maggi mee quite a lot, but let's just imagine today, if you ever cooked Maggi mee before, have you guys ever ran into a situation where you're like super damn hungry and the only source of food is going to be Maggi mee? If you ever had that situation before, right? Which I have had 1001 times, right? I realized that in order to get the fastest way to get my Maggi mee cooked, right, is actually to use less amount of water compared to usually where I use damn a lot of water. Now today, if I use less amount of water, right, and when I start heating it up, under the fire here, right, what I notice is that the less amount of water that is being heated up will reach boiling point much faster. From here, I know for a fact that it is much easier to heat up little water compared to more water. So in terms of heat capacity, or sometimes known as thermal capacity, I could say that the heat capacity or thermal capacity of the little water is less than the heat capacity or the thermal capacity of the pot with more water. Today, whenever you talk about heat capacity, right, you just have to understand whether it is easy to heat up or it is very hard to heat up. And nonetheless, obviously, the heat capacity of less water is going to be much less. So if you look at the first part of my statement here, you see that heat capacity is an extensive property of matter, meaning that it is directly proportional to the size of the system. For example, a small pot of water will require less time to heat compared to a big pot. We say that the water of the smaller pot is said to have a smaller heat capacity. Now, today, I want you guys to remember it in your mind, guys. Whenever we talk about heat capacity, it's just the ability for it to heat up fast or to heat up slower only. When we say something has a very high heat capacity, it means to say it is very hard to heat up. When we say something has a very low heat capacity, we say that it is very easy to heat up. Now today you can copy this first, but I'll explain a little bit more to you guys later on, guys. Copy everything from this here. I'll give you guys 1 minute. Then we move on to specific heat capacity. That is where the calculation is for most of your IGCSE questions. Just copy this down real quick in 1 minute. Okay. Everyone done copying, right? Anyone not done copying yet? Yeah, I'm just going to assume everyone is done copying, yeah? So moving on to the more important part this week here is definitely going to be specific heat capacity. Just now, when we talked about heat capacity, we basically said that if something has a very high heat capacity, it's hard to heat up. Something has low heat capacity, it's very easy to heat up. Right? Today, when we talk about specific heat capacity, we're specifying different materials with different heat capacities. Now, today, if you think about different materials, you definitely think that some materials are much easier to heat up versus some materials that are much harder to heat up. For example, today, if you ever try to burn a metal rod before, you'll realize that if you put the metal rod on top of the fire, very fast, the heat is going to travel upwards through conduction and it's going to heat up your fingers, and naturally you will let go, right? Comparatively, if you put the same under the same heating source, or you put water on top instead, you realize that you can dip your fingers in the water for a much longer period of time compared to the metal, and the water, the temperature of the water will still not be as hot as it used to, right? So from here, you have to understand that different materials will have different heat capacity, specific heat capacities. For example, the most common example that I always use is, let's imagine today I have 1 kg of water here versus another kg of something else, metal. Let's say we have 1 kg of aluminium here, right? So we know for a fact that metals are much easier to heat up compared to water, right? So if let's say today I put them both under the same heating source, right, I know for a fact that the metal is definitely going to be much easier to heat up. And if I want to go into numbers here, the reason why metal is much easier to heat up is because they have a much lower specific capacity. Now, in terms of the textbooks, right, they tell us that aluminium has a specific capacity of 900 joules per kg degree Celsius. Now, based on the units itself, you should be able to tell the story of what is going on. If we analyze the units today, 900 joules is basically energy, right? In this scenario here, it is obviously going to be the heat energy, right? Today, if I see that this is 900 joules per kg degree Celsius, it basically tells me that for every 900 joules supplied to the aluminium, 1 kg of the aluminium will raise the temperature by 1 degree Celsius. So let's imagine today, if this heat source gives off specifically 10,000 joules of heat energy. From here, if I understand that this heat source gives 10,000 joules of energy, and I also understand that the aluminium is only 1 kg, right? It's only 1 kg. I know for a fact that based on mathematics, right, this 1 kg of aluminium will raise roughly by 11 degrees Celsius if I supply it with 10,000 joules of heat energy. Now, water, on the other hand, has a much higher specific capacity. Water has a specific capacity of somewhere around 4,200 joules per kg degree Celsius. Now, looking at the units itself, it is yet again supposed to tell me a story that for every 4,200 joules supplied to 1 kg of water, I can only raise it by 1 degree Celsius here. So yet again, if let's say I'm heating it up under the same heating source, right, and I can only supply 10,000 joules of energy here, obviously what's going to happen is this water will raise somewhere around I don't know, maybe 2.3 degrees Celsius. I don't know, I'll do your own calculation, all right, somewhere around there. Yet looking at these numbers itself, I can clearly see that now today, if I heat up aluminium versus water, aluminium will heat up much faster simply because it has a much lower specific heat capacity. Now, before I proceed on, anyone don't know what I'm talking about? You basically have to understand that specific heat capacity tells us how much energy is needed to raise 1 kg of a substance by 1 degree Celsius. Anyone don't understand what I'm talking about? Anyone wants me to repeat any specific part? Good. If everyone can understand what I'm talking about, then it will be much easier here. From here, you can understand that of course, in your IGCSEs, they love to ask this. In your IGCSE, you can at least expect 1 to 2 questions in your paper 2. You can sometimes expect 1 to 2 questions, sub-questions are in your paper 4. Okay. Now, in terms of specific capacity, there is a super duper important formula which everyone should know. And the formula is given as Q equals to MC theta. Now, this Q here basically stands for heat energy, which is measured in joules. This M stands for mass, which is obviously measured in kg. This C stands for specific heat capacity, which is obviously measured in joules per kg degree Celsius, right? As I stated here. And this final thing here, this theta thing, theta is, for those who are confused with this symbol, it's supposed to be drawn like this, you know, like a 0 with a cross in between, right? This is what we call theta. Theta is basically the change in temperature, guys. Very important. It is the change in temperature. It is not temperature, because in your question, they will actually try to confuse you guys. They'll give you like the starting temperature and then they'll give you the ending temperature. Then some students will use the starting temperature. Some students will use the ending temperature. You're not supposed to use either. You're supposed to use the change, the difference in temperature. For example, if it starts off at 10 degrees Celsius and reaches to 30 degrees Celsius, the change is 20 degrees Celsius. Or if it starts off with 50 degrees Celsius and it changes to 100 degrees Celsius, the change is 50 degrees Celsius. Very important. Students always get this wrong. Okay, very, very, very important. Okay, so of course, from here, you know, usually if we talk about this in the physical classes, right? Students, they always have a hard time remembering the units or the definition of specific capacity, which is also very, very commonly asked in IGCSEs. Among the 10 years that I've seen so far, I think maybe like 4 to 6 years, they ask you to define what specific capacity is. I'll teach you how to define specific capacity based on the formula itself. And pay attention, guys, this same technique can be used across every other thing that requires a definition, guys. Today, if I want to define specific heat capacity here, first things first is I want to make specific capacity the subject. Making specific heat capacity the subject here, C would have been equals to Q over M theta, right? Anyone not good with algebra needs me to explain this? I think you all should know how to rearrange C to the specific to the subject, right? Okay, so if you can arrange it into the subject, looking at the formula itself, you should be able to define it or somewhat bullshit your way through the definition now, because looking at this formula itself, specific heat capacity is defined as the amount of energy required to raise 1 kg of a substance by 1 degree Celsius. I repeat, this is actually very important. Pay attention. Specific heat capacity is the amount of energy required to change 1 kg of a substance by 1 degree Celsius. Anyone didn't get that? Anyone wants me to repeat? Okay, super important. Everyone must know how to repeat this. So from here, if you can repeat this, of course, looking at the formula itself, you can also determine what units is supposed to be long. Because like I mentioned just now, here is heat energy, right? So obviously it's going to be in joules. This is obviously going to be mass, right? So it's obviously going to be in kg. And this is change in temperature and thus degrees Celsius. This is how we come to the joules per kg degree Celsius in this part here. Now, this technique can be used across all the random things as well. Like for example, spring constant. No one remembers the units for spring constant, right? But everyone knows the formula for spring constant. F is equals to Kx, right? Spring's constants formula. If you one day you forget the units for spring constant, you can just simply rearrange it to F over X here. And of course, you know that it's newtons per meter, and thus the units for spring constant is going to be newtons per meter, guys. This same technique can be used across many multiple things as long as you remember the formula. So that's why I always tell the students, if you really don't get physics, you can really start off with memorizing all the formulas first. Try not to memorize it up because there is some reason and logic to all the units and all the stories it is, right? So, try to remember the formulas first, then from there you will be able to remember the units. From the units, you'll be able to remember the definition. From the definition, you'll be able to get the theory and so on and so on and so on. Try not to memorize that because I think biology and chemistry already require a lot of memorization, right? Try to understand physics. I think it will be much easier and of course more applicable in real life as well, as long as you understand it. Okay. Anyone's got any questions with this part here? Okay, if you have no questions, let me just take a screenshot here so that you can refer it later on WhatsApp, or you want to copy anything down. Right. Yeah. If you have no questions, then of course, looking at the notes itself, this is the important part, right? Yeah, it's basically everything I mentioned, just that it is in a more structured format. All right. Specific capacity, different materials will have different specific capacities. 1 kg of aluminium will require 900 joules of energy to heat up. 1 kg of water will require 4,200 joules of energy to heat up by 1 degree Celsius. The energy needed is equals to the mass times specific heat capacity multiplied by the change in temperature. The ultimate formula that you should remember is Q equals to mc theta. For those students who are having difficulties memorizing the formula, what I personally like to do when I was young and even at this age here, I'll always repeat the thing a few times. I hear it in my own voice and I'll be able to recall my own voice in the exam. Just say like Q equals to MC theta, Q equals to MC theta, Q equals to MC theta. And in the exercises later, it's always good habit to write down the formula before you attempt substituting the numbers in. That would definitely help in the long run as well. So, the problem is the students, they're always very lazy. They feel that, I already know, now, right? But you won't remember later on. Just try to write down the formulas as much as you can. Whenever the opportunity presents itself, write down the formula, say it in your head. It will definitely help much, much, much more in the long run, especially when you go for the exams. Okay. So, like I mentioned just now, by definition, specific heat capacity of a substance is the amount of energy needed to change the temperature of 1 kg of the substance by 1 degree Celsius. Of course, you don't have to go word by word at all. You can try to freestyle it as long as you can define it with accordance to all the important things here. It's just a matter of structuring your words, right? Using the formula Q. C equals to M over theta here, right? You don't have to follow word by word. Yet again, this is not an English exam. It is physics. You don't have to follow it word by word. All right. And high specific capacity obviously means to say it needs a longer time to heat up or cool down. For example, if you ever boil hot water before, you realize that it takes much longer for it to cool down compared to the pan, the metal on the side, right? It's because for high specific capacities, harder to heat up, but harder to cool down. Low specific capacities, very fast you can heat up, very fast you can cool down, right? And thus, different materials have different specific capacities. You can see here, aluminium has 900, glass is 800, copper is the lowest, obviously. Gold is even lower, water is definitely the highest, right? Talking about the specific capacities, you can somewhat relate it totally not to physics, like in real life as well. Like there's this saying in Chinese, what's it called? How do they say it? I can't remember the exact wording, but it basically says like, if you climb very fast, you'll fall very fast as well. It's always better to have a steady incline so that when you reach the top, you're more stabilized before you start tumbling down. It's the same like life. Like a lot of people, they are handed a bunch of money, like suddenly they win the lottery. It's like a very fast jump in the wealth, right? But very fast they will jump down as well, because just like physics, if you have low specific capacity, you take a very short time to get rich, but you take a very short time to get poor as well. So totally not related to physics, but I think it's quite important to understand that stability is more important than speed, right? Yeah, but just my 2 cents comment. Copy everything down. Then after that, we'll attempt some of the questions together. I don't think I can finish this chapter today, by the way. So we'll most likely bring it forward to next week as well. But copy everything down first. Okay, everyone. Is everyone done copying? Yeah. If everyone is done copying, let's circle back to this part here, guys. Just now I told you guys to just copy down the formula first for this part here. Thermal capacity, it actually has the same concept of specific capacity. Today, if I rearrange thermal capacity, I can say that Q is actually equals to thermal capacity multiplied by theta here, whereas specific heat capacity is Q equals to mc theta. Today, the main difference between thermal capacity and specific heat capacity is that one has mass and one doesn't has mass. So you can see here that this and this are somewhat aligned, and then this and this is also somewhat aligned. The only thing that is missing is going to be this part here, right? Very important as well, guys. Why is it so important is because that it doesn't come up as often in IGCSEs. And because it doesn't come up as often in IGCSEs, what happens is a lot of students, they lack the practice to do it, and they always forget that there is such a thing here. Today, if you can remember specific capacity, which has a formula Q equals to mc theta, you must also recall that thermal capacity has almost the same formula, just that it's missing the mass component. All right, so Yeah, this arrangement here is basically thermal capacity is equals to Q over theta. But if you rearrange it into Q, you'll get something like this. Q equals to thermal capacity multiplied by theta here. All right, everyone. Anyone not clear with what I'm saying? You all are awfully quiet today. It seems like you must be going through some kind of a holiday depression. But please make sure you understand everything. This chapter is actually very important. It's the only calculation chapter in your thermal physics, guys. All right, everyone. Okay. Yeah. If everyone is okay, then yeah, let's take some time to do these questions here. There's going to be 5 questions at the bottom here, guys. You'll find that question 1 to 4 is relatively easy, whereas question number 5, it actually requires some thinking and some understanding of thermal equilibrium. All right, I'm going to give you guys probably 15 minutes to attempt the 5 questions here. Please make it a habit to write down your formulas while you're doing exercises, because trust me when I say this, it will help. And I've helped many students understand this already. Please do it before it's too late. Okay, 15 minutes, everyone. Please do the 5 questions at the bottom here, and we'll discuss the answers. How many of you guys are done with question 5 already? Just want to know. Or how many of you guys are attempting question 5 already? Okay. All right. Yeah, question 5 is going to be a bit hard. I'll give you guys like probably 2 more minutes to attempt it. Then after that, let's go through it together. Okay, everyone. I think you had sufficient time attempting some of the questions. Let's go through it together real quick. Okay, so like any other calculation questions, first and foremost, you must always identify what information is given to you first, right? Look at this information here. This is obviously the mass. This is obviously the change in temperature, and this is supposed to be the specific capacity. They're asking about how much heat energy is needed. So first things first is you're going to write Q equals mc theta here, which is obviously going to be 4 multiplied by 452 multiplied by 20. Press that into your calculator. 4 times 452 times 20 here. You're supposed to get a very weird number of 36,200 joules. Correct to 3 significant figures, guys. Like I always mentioned, your calculation cannot be more than 3 significant figures. Right. Then moving on to the next part here. Same thing as well. Identify your information. All right. This is obviously going to be your mass. This is the starting temperature of the thing. It's the starting temperature. So let's label it as temperature 1. What is the temperature of the water after this amount of energy has been removed? And this is obviously your specific capacity here. Now today, if I want to find out the final temperature, first and foremost, using this information, the M, the C, and the Q, I can find the change in temperature, right? So yet again, if Q equals to MC theta, theta would have been equals to Q over MC here, which is going to be 1.57 times 10 to the power 6 divided by 3 divided by 4,200 here. Press that into your calculator, and I think you would have removed 125. Is it 1.575 times 10 to the power 6 divided by 3 divided by 4,200 here? Yep, it would have been 125 degrees Celsius. The change in temperature would have been 125 degrees Celsius if it started off at 35 degrees Celsius, and obviously if we put it in the refrigerator, the temperature is supposed to change by 125, right? So at the end of the day, you're going to get negative 90 degrees Celsius, right? Of course, if we talk about a logical point of view, there's no such refrigerator that can refrigerate it until negative 90 degrees Celsius. It's just for the sake of calculation, guys. Also to test your understanding if you read the question properly. Some students, they give me like 100 over degrees Celsius. At the end of the day, I'm like thinking, which refrigerator makes it so hot, right? It's not a refrigerator if it's going to get hotter, right? So it's just a play of your understanding and what you're going to do with the numbers, right? Anyways, moving on to the next part here. I think these two calculations were quite easy. It's just M, this is C, and then this is theta here, right? So how much heat energy is obviously going to be Q equals MC theta. Press everything into the calculator and you will get 4,200 joules, guys. Right? Not much problem with question 3 and 4, I think. Right? Same thing here as well. This would have been Q. This would have been raised by 10 degrees Celsius, so it's theta. Then this would have been M. The specific capacity will be Q over M theta here, right? Which is going to be 8,400 divided by 10 multiplied by 0.2, which at the end of the day will still give you 4,200, but the units will be different, guys. You're supposed to see that there's a change in the units, and thus is going to be kg degrees Celsius here, right? How many of you guys got all 4 questions correct for the first part? Jay-Wei, you got everything correct? Nice. Meh. Oh, me. Oh, okay. Natalie, you got it correct as well. And Charmaine, you got it correct as well. Yeah, I still owe you a drink, Charmaine. But I've been trying to go on Grab, right? And then I don't see any of the boba teas, you know. Maybe I'll try something else. Oh, for those who are wondering why she got free boba, is because she scored an A for her recent test, guys. In the center here, right, you can always claim your free boba or treats or whatever in the form of monetary value or whatever. As long as you are able to score an A, you will definitely be rewarded for your hard work, because an A is not hard, right? But you definitely need to put in effort to get it, right? So for those who want a free boba or any free drinks, come claim it from me. Just make sure you take a screenshot. Does F count? F is gonna be, of course not. Are you crazy? Yeah, but please work a little bit harder for your physics. You will your effort will not go unrewarded, right? But Charmaine, I still owe you a drink. I've been looking at Grab, and then it seems like they don't deliver it here for some reason. Maybe I'll get something else for you, but I'll order it after class. Okay, I still owe you. But don't worry, I'll always pay my students, right? Anyways, moving on to the final part here. All right, question number 5. Oh, it's not just, you don't have to go to the center. I mean, as long as you score an A, I'll still deliver the Grab food from wherever and order it to your place. That's how we usually conduct it. You don't have to be at the center, right? As long as you score an A. Anyways, moving on to the final question here. Any or just drinks? Sometimes if the drinks are not available, I just send like Grab credits or Touch and Go credits to my students, and I ask them to go buy themselves something nice to drink. You know, yeah. It's the reason why I do that is just because I don't want your effort to go unrewarded. I always believe that, you know, if you put in some effort, you should be rewarded. Just like how when you score full A's in your IGCSE, you should definitely use it as a bargaining chip to your parents to buy something nice. You know, that's usually how you should do it. But hey, don't let anyone else tell you otherwise. Okay. Anyways, moving back seriously to this question here, right? Just yeah, money. I'll send you money as well if you want, if you prefer. Yeah. Anyways, back to this, right? This question here is a bit harder to do because there's a little bit of application of how you're supposed to use the Q equals MC data. So far, I think out of the 100 students or so that have come across this question, I think maybe like less than 5 of them were able to do it on their own. And then usually the rest of them will require some explanation, which is nothing new, right? It's just that it's hard, and you guys were never exposed to these kind of questions, right? But anyways, if you look at this part here, let's draw a simple understanding of this first. Let me extract all the information first, and I'll draw it in a visual format here. So basically, there is a steel ball, right? This steel ball is like 0.02 kg. It's starting off with temperature at 95 degrees Celsius. It is placed into water, right, which is 0.2 kg, and starts off with 24 degrees Celsius here. Then after that, they say that the specific heat capacity of steel is 450 joules per kg degree Celsius, and this water here has a specific capacity of 420 joules per kg degree Celsius. Right. Okay, so these are all the information we need. Okay, and we know this part. Okay, so if we look at this part here, right, we understand that obviously if I put a hot metal ball into water, what's going to happen is the temperature of the metal ball is going to decrease and the temperature of the water is going to increase. This is what we call thermal equilibrium. Thermal equilibrium is basically like, you know, if you ever had your hands cold and then you hold your boyfriend or girlfriend's hand, then you feel like it's a bit warm, right? It's because the heat from his hand is passing on to your hand here. This is also a form of thermal equilibrium. If you watch all the stupid movies where they're about to die in Antarctica, right? Then after that start, oh, that can be arranged. And if the single boys here can get her number, it's in the group chat. You can text her anyway. Anyways, if you watch all the stupid movies in Antarctica, right, they say that sometimes if they run out of heat or fire or wood to burn, right, then they start taking off their clothes and then they start hugging each other to sustain, right. That is one of the reasons. The reason why they do that is because they're trying to share the internal body heat so that they don't die from hypothermia. I can't remember what's the term, but basically you get too cold and then you die. I can't remember the term, but that's the theory there. They want to share the heat between them so that they don't die, right? This situation here, it will be the exact same scenario as well. The first thing you must understand in this calculation here is that you must understand that the energy lost by the ball will be the energy gained by the water here. Okay, so first part, the most important thing for thermal equilibrium is that the energy lost by the ball, the heat energy lost by the ball, will be the heat energy gained by the water here. From here, you can actually start formulating your stuff and you'll get something like mc theta is equals to mc theta. From here, you're going to start substituting in 0.02 of the ball and a specific capacity of 450. Multiply by the theta. The theta is the tricky part, guys. You pay attention. The theta, some students, they will like to write 95 because they think that it's going to be 95 going to 0 degrees Celsius. But the real answer is you do not know what's the final temperature of both of them when they are in equilibrium. But you know for a fact that the temperature of the steel ball is definitely going to decrease. So from here, the first thing you're going to write is 95 minus x law, right? This 95 minus x indicates that the ball is going to decrease in temperature, but change by how much you don't know. But you know that it's going to reach a certain temperature x. So you just write 95 minus x law. This will be your first half of the equation, which is equals to the mc theta of the water, which is yet again very straightforward. You substitute the mass in, you substitute the specific capacity in, but yet again, when it reaches the change in temperature part, you yet again don't know what the temperature change is, but you know for a fact that the temperature of the water is going to increase instead, right? If the temperature of the water increases, is that you don't know to what temperature. Always remember that theta is change in temperature, right? So you don't know how much more, you write x minus 24. From here, you will have found that this equation is equals to this equation here. From here, it's just a matter of algebra, and you should be able to find your x. Everyone do this right now. Tell me what your x is and copy this down. Whoever has found X already, please let me know. I want to see. Oh, very good, Jen Lim. Fast and accurate once again. Yep, you're correct already. Negative. Shermaine, I think you did something wrong with your calculation. How can it be a negative value? Oh, oh, yeah, that's correct. Very good, Natalie. That is correct as well. Good, Lane. Jerry. Jerry, are you stuck? You need me to tell you how to do it? Oi, how can you come to physics class without a calculator? Oi. All right, I'll do your calculations later on. Kunming, can or not? Kunming. Yes, correct. Very good. It's 24.75. Right. Okay, so this is that. Okay. Yeah, very good. Then the final part before we end the day here, basically, if you look at this kind of questions here, right? Like I mentioned previously, right, in your power formulas, guys, if you all recall the power formula, power is supposed to be energy over time. I think I mentioned this before, but I'll mention it again. In school, what your school teachers like to tell you, it's instead of energy over time, they like to say that it is work done over time. Now, that is definitely not a wrong statement, but it is not the entire truth. This energy can be any form of energy. It could be work done, it could be kinetic energy, it could be potential energy, and in this scenario here, it could be heat energy. Now today, if you want to understand what is going on in this formula here, you basically, you know, like how we know that how much heat is going to be supplied here, it depends on two specific things, right? Number one, how much power is supplied to this heater, right? And how long this heater is heating this thing here, then we'll know how much heat energy it is now, right? So from here, if we want to find out how much heat energy is being supplied to this metal block here, we can rearrange the formula to power times time is equals to heat energy, right? And in this scenario here, since we're talking about heat energy, it's going to be actually power times time equals to heat energy, right? From here, power times time is going to be equals to mc theta, and this gives rise to the whole formula of how we convert electrical energy to heat energy. Basically, this next part here that we're supposed to talk about is basically understanding how electrical energy is converted into heat energy using the formulas itself. And it always starts off with understanding that power is equals to energy over time. Power times time is equals to energy, then power times time is going to be equals to mc theta, right? So depending on how much power is applied to this heater and how long we heat this aluminum cylinder here, we'll be able to determine how much heat energy is supplied to the aluminum cylinder, right? So from here, you know, heat energy can be converted from other forms such as electrical, potential, and even kinetic energy. In this scenario here, if we were talking about electrical energy, is basically power times time is equals to mc theta. And the units will still be the same, guys. Power is still going to be in watts, times is still going to be in seconds, and MC data is still going to have the same exact units, right? Can you guys copy this formula down? You can copy this one or this one, it doesn't really matter, right? Then after that, this will be your homework for this week, guys. Finish up question 1 all the way until question 3. We'll discuss the answers next week. Then we'll move on to latent heat of fusion and latent heat of vaporization. Yeah, way it's just 3 questions. I hope the heartbreak wasn't your sadness from having homework. Yeah, copy this down, and then we're done for the day already. Okay, guys, if you're done with copying, that will be it for today. If you have any questions, you're always welcome to stay back. But if you have no questions, that'll be it for today. I'll see you all next week. Welcome. Goodbye.